In this video, you will be learning about kinetic energy. Our essential question is, what does it mean to do work? By the end of this video, you should be able to differentiate between kinetic and potential energy, calculate the kinetic energy of an object, and relate work and energy changes. Kinetic energy is defined as the energy of motion. The equation for kinetic energy is 1/2 times the mass times the velocity of the object squared. In this example, we have a 3,900 kilogram truck moving at 6 meters per second, and we want to find its kinetic energy. So we know that the formula KE equals 1/2 m times the velocity squared. And the mass of the object is 3,900 kilograms, and the speed is 6. So when we plug these values into the equation, we get that the kinetic energy is equal to 70,200 joules. The work energy theorem states that the total work done on an object is equal to its change in kinetic energy. We need to keep in mind that this is the total work done on the object, not just the work that you are doing. For example, we have a student lifting a 50 kilogram box at a constant speed for a distance of 3.0 meters. How much total work was done? Well, the student is doing work because they are lifting the box. However, they're doing work against gravity, so gravity is doing negative work. Because we're told that this box is being lifted at a constant speed, we know that the kinetic energy of the box is not changing. This means that no total work is done. You are doing work and gravity is doing negative work, but the total amount of work is 0. How much work is required for a 74 kilogram sprinter to accelerate from rest to a speed of 2.2 meters per second? Now we know that the work is equal to the change in kinetic energy. So work is equal to 1/2 times the mass times the initial velocity or final velocity squared minus 1/2 times the mass times the initial velocity squared. Now if you want to, you can leave it in this form. However, we could also factor out the 1/2 times the mass, and then we would have 1/2 m times Vf squared minus Vi squared. However, keep in mind, if you do it this way, Vf squared minus Vi squared is not equal to the change in velocity squared. And you can FOIL that and see that that is not the same thing. So if we plug into this, we have work is equal to 1/2 times the mass of the sprinter is 74 times the final velocity is 2.2 minus the initial velocity is 0 here. And we get work is equal to 180 joules. A student lifts a 4.10 kilogram box of books vertically from rest with an upward force of 52.7 newtons. The distance of the lift is 1.60 meters, and we're asked to find the final speed of the box. Now we need to remember that there are two forces acting upon the box, gravity and the applied force of the student. So for the work due to gravity, remember, work is equal to force times distance. However, the force being applied by gravity is the weight, so mg times the distance, and the mass is 4.1. Acceleration due to gravity is 9.81, and the distance that it's being applied over is 1.6 meters. This gives us a total of negative 64.3536 joules of work, and it's negative because the direction of the force and the distance are opposite each other. Then we have the work from the applied force that the student is applying. And again, work is equal to force times distance, but in this case we're actually given the force of 52.7 newtons, and the distance again is 1.6. This is a positive value because the force and the displacement are in the same direction, and we get 84.32 joules of work. Now, I didn't round either of these to significant figures because we're going to be using them. We want the total amount of work done, which we'll get by adding those together, taking into account their sign. So the total work ends up being 19.9664 joules. And I know that the work total is equal to the change in kinetic energy, which is equal to 1/2 mass times the final velocity squared minus the initial velocity squared So now I have 19.9664 is equal to 1/2 times the mass of the object was 4.1 times, I'm looking for the final velocity squared, or the final velocity, which in the equation is squared, minus the initial velocity. It tells me it's starting at rest, so I know the initial velocity is 0. When I solve for that, I end up getting VF is equal to 3.12 meters per second. And it has 3 significant figures because all of my data had 3 significant figures. So remember, kinetic energy is equal to 1/2 mv squared, and the total amount of work done is equal to the change in kinetic energy.